We talked about rectifiers. Basically, the figure on the left is ReLU. The figure on the right is parametric ReLU. And you can have the parameter AI to be channel dependent or filter dependent. It means that per each filter, you're going to have a different activation function that you want to learn. And we came up to the conclusion that, yes, it actually slightly improves our accuracy and basically drops our error rates. Then the question is, how are you going to initialize your filters when your activation function is a rectifier? And we said we are going to look at the variance of the response in each layer, and that's going to help us come up with an idea of how to initialize these parameters. Usually the bias is going to be initialized to 0, so that we know how to initialize it. We know that we are going to initialize W's with a distribution. Probably it's going to be normal. That's going to have a mean 0. And we want to figure out what's the proper variance for these weights or for our filters. We said we are going to flatten everything out. We take a k by k window of our image, and the k by k window is going to be k squared pixels, and they're going to have C channels. For instance, the first layer is going to be red, green, blue, and the other layers are going to be, I don't know, 47 channels. So we are flattening everything out and putting everything in one long vector, and n is going to be basically k squared C. And that's the number of connections of a response. D is the number of filters that you have, and it's going to correspond to the number of pixels of your next layer. Not the number of pixels, actually the dimension of the pixels. Because each pixel is going to have dimensions. It's going to be a vector. And then we said convolution is nothing but matrix vector multiplications. That's our weight, that's our bias. Our bias, we are going to initialize it to zeros. Now, how is this layer related to the previous layer? They are related to each other by an activation function. Basically, the output of a linear combination of your inputs is going to go through a nonlinearity. In this case, our nonlinearity is ReLU. And then it's going to give us XL, the input to the next layer, or the input to the current layer, according to these indices. And the way the dimensions or our filter sizes match is that the filter size of the output of the previous layer is going to be the number of channels of the current layer. So that's how these guys are related. So basically, whenever you have n, it has to be an L or CL and DL, but for ease of notation, I'm just using that. N is just k squared C, D is the number of filters. But these are per layer. So if you want to be really careful, then you keep the index L all the time. And then the idea was to look at the variance of the response, basically variance of YL. We know that YL is one element of the output, so it has a distribution. WL is an element of your capital WL. And we want to know how to initialize them independent from each other. So each entry of your W is going to get initialized independently. It's going to be identically distributed and independent. But then there is a summation here over n. Whenever you are doing matrix vector multiplication, there is a summation over n, and then you're summing the entries of your vectors. Basically, it's a dot product. That's why you get NL out. And then you have variance of WL XL. Now, I hope you spend the time to look at the variance, the formula for the variance of product of two random variables. And if you just Google it, this formula is going to come up. It's one of the formulas that is going to show up. So what we are doing is just writing variance of WLXL as variance of WL and expected value of XL squared. Then we know that we want to initialize our weights such that they have a mean 0. So that we are going to assume. Therefore, the variance is equal to expected value of your random variable squared. Basically, the second moment is going to be your variance. If this was true, then initializing would be easy. You would just initialize it by square root of 1 over n. But this is not true. For ReLU activation, because if you look at it, XL is a nonlinear function of your YL minus 1. So this is not true. What is true is that the expected value of XL squared is 1/2 the variance of YL minus 1. So half of the times it's 0, and the other half is the same as your variable. So it's going to be 1/2 of the variance. That's what you get for ReLU. Now you go ahead and plug this formula here instead of expected value of XL squared. So we are going to replace that. And this is what you get. Variance of YL is 1/2 coming from this formula. NL is what you have up there. Variance of WL is here. And variance of YL minus 1 is coming from here. So is this clear? Any questions so far? Now you keep doing that for all of your layers. Basically, variance of Y2 is equal to variance of Y1 times whatever that you have at that moment. And then you keep doing that in an iteration. That's going to give you the variance of your last layer is equal to variance of the current layer. I mean, the first layer, the first input, and then a product of these 1/2 and variance of WL. So the problem with multiplying many numbers, as I mentioned in the previous session, is that it's either going to explode or it's going to go to 0. If it explodes, it means that your outputs are getting huge, and then it's getting out of control. If it vanishes, you are always getting a constant. You're always getting a 0. To avoid that, does anybody have any idea what we need to do? So we want to avoid exploding. Yes. So Jacob has the right answer. You want to make all the numbers close to 1. So you want to make these numbers that are being multiplied by each other to be close to 1. So that's what we are going to do. We are going to say, let's assume this is 1, or let's try to make it as close as possible to 1. And then that's going to give you your initialization. If your variance times a number has to be equal to 1, so the variance of your weights has to be 2 over NL. It's coming from this part. And then the standard deviation is going to be a square root of 2 over NL. So this is the proper way of initializing convolutional neural networks with ReLU activation. Any questions so far? So prior to this work, people were using just a constant standard deviation. And the problem with that is that this formula is not going to hold, and the variance is either going to explode or go to 0. So the variance has to depend on the number of, on your filter size and the number of input channels. Basically, it's depending on the filter size and the number of the input channels. But this is not game over. This is when you are pushing forward through your neural network. Things could go wrong when you go backward, when you're taking your derivatives, when you're doing backpropagation. And that's going to be either exploding gradients or vanishing gradients. If your gradients explode, then you're always jumping around in your optimization landscape. And if your gradients vanish, then you have 0 gradients and there is no learning happening. So you are always going to be stuck where you are starting. So no learning is going to happen. So backpropagation matters. Let's see what happens in the backpropagation pass. Delta XL is going to be the derivative of your loss function with respect to XL, which is a pixel at your input. It's going to be WL hat times the derivative of your loss with respect to YL. So these are just derivatives. Derivative of the loss with respect to the input pixel, derivative of the loss with respect to the outputs. And WL hat is going to come from WL by reshaping it, maybe transpose, and then basically flipping your filters left and right, looking at it in a mirror.
So I have a question about that because I've seen backpropagation briefly with convolutional neural networks, and I've not understood that part. Do you have an intuitive explanation for that, or a simple, maybe like intro textbook or something which goes into those details?
So what I have online, I shared the link with everybody, I think the first session. In that link, that's for 1-by-1 convolutions. That's for a fully connected one. How about you take that and then try to extend that? But then it's very easy. The thing that you're doing is take the derivative of YL, the derivative of your loss with respect to YL. And then these summations, if you expand them, you're going to see how WL is related to WL hat. So you just have to expand this. There is a summation over all of these entries. And then you take the derivative of your loss with respect to this pixel and see what happens. But everything is coming from taking the derivative of this guy. It's a chain rule. So if the pixels were 1-by-1, if your windows were 1-by-1, then you know that the derivative of XL, of your loss with respect to XL, is going to be WL transpose times the derivative of YL, basically the derivative of your loss with respect to YL. But now you have a bunch of other pixels. So there is another summation. So it has to do with transposing this guy, WL. So I don't want to get it into the heavy machinery of this, because then it's going to be one slide for itself. But I think you guys can do it at home. It's not rocket science. It's just taking derivatives and using chain rule. So now what are we doing? We are taking a look at one of the pixels, and we are taking the derivative of the loss with respect to that pixel. And each pixel is in RC. It has C channels. So same thing is going to happen for the loss. It's going to be in RC, the derivative of the loss. These are just gradients. The gradient is going to have the same dimension as your number of variables, in this case XL. So that's just one pixel. And then that pixel is going to get affected by K by K pixels of the output. And the output is going to have D channels. Now the question is, what is n hat? N hat is going to be k squared by d. Similar to n, which was k squared by c, n hat is going to be k squared by d. And as I said, WL hat, you're going to get it from reshaping W. And to make sure that things are at least correct, as for the big picture, we can look at the dimensions of WL hat. This is C by n hat, which is going to be C k squared by d. So let's remember that number. And let's go back here. W was d k squared by c numbers. So at least you have the same number of numbers. And that's going to give you some comfort that things are correct. But in the end, what's happening is just a reshaping of W. So you are doing a transpose for the channels, and then you are flipping your filters left and right. You're looking at it in a mirror. So that's how you do backpropagation, and things are linear. And I'm sure if you write out the summation on a piece of paper, you're going to see this relationship. And it's actually a very good exercise. I highly recommend it. Any questions so far? Okay, then. What happens when you have the activation? You're going to have to take a look at this one, this formula here, and shift it one layer forward. So it's going to give you xl plus 1 is equal to f of yl. Now you take the derivative of your loss with respect to xl plus 1, write down the chain rule, and then you get the derivative of your activation out on your yl times the derivative of your input, which is basically you are thinking backwards now. But it's coming from this formula and writing down the chain rule. This is xl plus 1 is equal to f of yl. Now you write down the derivative of your loss with respect to xl plus 1. A derivative of your activation is going to come out because of the chain rule. And then the derivative of your loss with respect to yl. So this formula is coming from here and from the chain rule. So that's another exercise. Just write that down more carefully. So now we are in a good shape. We know how things are backpropagating in terms of loss through the nonlinearity and through these linear operations. The linear operations are happening this way, and all you are doing is reshaping of your weights. And through the nonlinearity, you get the derivative of your nonlinearity out. So many people think that backpropagation is just chain rule, but it's more than that. Can somebody tell me why is it more than that? So that's one thing. So we are just reshaping, which is coming from the chain rule. So that's just the chain rule. Yes, which is just a chain rule. It's something more than the chain rule. Why is it fast? Is it looking forward in X? You are getting close. So do you guys know about this concept of memoization? It's not memorization, but memo. I hope I'm writing it correctly here. So you are sort of memorizing some of the operations that you did when you were doing your forward pass. So when you are doing your forward path through your neural network, there are a bunch of things that you're calculating. Like here, you're calculating YL. When you are here, you're calculating XL. So there is no need to recalculate them or recompute them. There is no need to do these operations once more. You just memorize the value of YL. Why do you memorize it? Basically, you're storing it in memory. Why do you memorize it? Because here you need it. When you're doing your backward pass, you just read from memory. And that's why things are fast. The rest of it is just scalar vector multiplication and matrix vector multiplications. So it's going to be as fast as your forward pass. Otherwise, you would need to compute YL each time, which is not efficient. So is it clear? Exactly. So it's caching it. So there are two things for backpropagation and why it's nice. One is the chain rule, and that's from the mathematical perspective. And from implementation perspective, what computer actually sees and does is this concept of memoization. So backpropagation is memoization plus chain rule. Okay, that was a good concept. That's a parenthesis that we opened. Let's close it. And let's go ahead and take a look at the expected value of the derivative of the loss with respect to YL. So the derivative here, the one that you see, is going to be either 0 or 1 with equal probability, and it's independent from the one on the other variable. It means that its expected value is 1/2 the expected value of delta XL plus 1. And we know that the expected value of delta XL plus 1 is 0. They're going to have mean 0. Now what? We can take a look at the second moment, which is going to be equivalent to the variance. And once again, we are using the fact that it's either 0 or 1 with equal probability, and that's going to give you 1/2 variance of the other guy. So this 1/2 term is showing up left and right when you are doing forward pass and when you're doing backward pass. So now you take that and plug that back inside. Actually, you are taking the variance of delta x. There is a summation here of size NL hat, and then variance of WL, because we know that WL hat and WL have the same entries. So it's just going to be WL. It's not going to be WL hat. They have the same entries. And then it's going to be variance of delta Y. And then we are going to use this formula and plug it inside variance of WL, and that's what you get. And then you do a, basically you go backward. You know that variance of delta x2 is relevant to variance of delta x3 and so on. You do your iterations. And again, this entry here has to be close to 1. And that's going to give you another way of initializing your neural network. It turns out, what is the message? You can either use NL hat or NL to initialize. But it turns out that in the end, these are going to be different by only a constant. The variance of your output, if you use this formula, then the variance of your forward pass is going to be different from this variance by a constant. And a constant doesn't make sense, so it's not exploding or it's not vanishing. And what is NL hat? NL hat is all the way up here. NL hat is K squared DL. And these are different. NL hat is a different number from NL. Does that answer your question? Okay, perfect. So you can either use NL hat to initialize, or you can use NL to initialize. In the end, it doesn't matter much. Things are not going to explode or vanish, either in the forward pass or in the backward pass. Now, we did a lot of work to reach here. You can do the same algebra and come up with the right initialization for where you have parametric ReLU. For parametric ReLU, these are the final equations that you're going to end up with when you go through this algebra. So if you're using parametric ReLU, there is 1 plus a squared that's appearing in your formulas. If a is 0, you go back to ReLU, and these two formulas are the same as the ones that we discovered here. here, and here. So what is the message here? The big picture. I think we went into a lot of details, but let's now come back and look at the big picture. The big picture is that activation function matters when you're doing your initialization. Initialization is not a trivial task. Initialization matters. Activation matters. And the problem comes from either in the forward pass or the backward pass when you're multiplying a lot of numbers together or a lot of matrices together. So things are gonna either explode or vanish, and you want things to behave nicely. I think this is the most technical slide of this course that we're gonna go through. But it was a nice exercise to go through these details. In the end, what you're gonna remember from this paper are these two: how to initialize it, and you're gonna use this formula to initialize your neural network. But if you change your activation function, then you have to be careful. Any questions? We learned a lot of nice techniques. One is that we learned about ReLU, and these are big steps in the deep learning literature. Before ReLU, things were not converging, things were not behaving. We learned about dropout. We learned about batch normalization, and we learned about how to properly initialize our neural networks. So these are big steps. Without these, it's gonna be really hard to train neural networks. Okay, if there are no questions, let's move to the next topic. Does leaky ReLU change the initialization? Leaky ReLU is similar to parametric ReLU, but then those parameters are fixed to a constant. Let's say 0, 0, 1, small constant. But then the formula that you're gonna use, I don't want to go back to the previous, yes, I can. This is the formula that you're gonna use, but A is gonna be a constant. For parametric ReLU, this guy is channel dependent. Does that answer your question? Would you ever use different activations for different layers? I would say yes. Sometimes you want your, actually, let's look at the final activation of a binary classifier. The final activation is going to be a sigmoid because you want things to turn into probability. So for the final layer, you're using a different activation. And if you think about this parametric rectifier, okay, that's a great question. How would that affect the initialization? It wouldn't. If the only thing that you're changing is only one layer, then your gradients are not going to explode or vanish, or your forward pass is not going to explode or vanish because it's just one activation that you're changing. The problem arises when you're doing this multiple times and your network is deep. Then you're multiplying a lot of numbers together, and things could either vanish or explode. Does that answer your question? Okay, great. Any other questions?